All right, guys, this is an example of the second type of chi-squared test. It's the first one discussed in section 2 of chapter 11. It's called the chi-squared test for homogeneity. And as you can see, I'm going to work out the example on page 732, problem number 3 from the chapter review. Part A asks you to make a two-way table given all of the information that's in the problem. If you read the problem, it talks about 3 different types of treatments that are given in this scenario: stress management, exercise, and the usual care, and they record whether or not the patient has had a cardiac event. So filling out the numbers, let's see, there were 33 in the stress management group, and out of those 33, 3 had a cardiac event. So that's 30. Then there were 34 in the exercise group. 7 of those, which makes this 27. And 40, 12, 28. And filling out the totals. All right, so that's part A. Part B, what's the success rate, or what are the success rates of the 3 treatments in preventing cardiac events? All right, so the 3 treatments, that means that 33, 34, and 40 are going to be our 3 denominators that we're looking at. And so the success rate would be 30 out of 33, which is 0.909. Then 27 out of 34, 0.794, and 28 out of 40 is 0.70. So stress management, exercise, and usual care. Now, homogeneity means the same. So the whole point of a chi-square test is to determine, are the proportions the same for, in this case, the 3 groups, or are they different? So the null is that the proportions are the same, because remember, the null hypothesis is the no effect or no difference hypothesis. The alternative will be that there is a difference in the proportions. So that's what we're going to do now. Part C asks, is there significant difference among the success rates for the 3 treatments? Give appropriate statistical evidence to support your answer. So this is where we're actually going to carry out the test. We name it chi-squared test for homogeneity. All right. The null hypothesis. Sometimes students have a hard time figuring out the null and alternative for these. You have to put it in context, because the book tells you what it is in generic form, that there's no difference in the proportions. The alternative is that there is a difference in the proportions. So in this case, we'll say there's no difference in the actual proportions of cardiac events for the 3 treatments. The alternative is that there is a difference. And just like we were doing earlier in the chapters, you can put ... You don't have to finish that sentence. All right. Now, the conditions. Random, stated in problem. oh wait, I'm sorry, this is an experiment. So I'll say stated in problem that random assignments took place. Let's see, it's not normal, because remember we said in the last video, chi-squared tests, chi-squared curves are not normal. We put large sample size. Is it a large sample? And I haven't checked it yet, but I'll show you how to check it in just a second. I'm going to assume for right now that all expected counts are greater than 5. Or at least 5. And then independent. Experiment satisfies independence. All right. Now, we've already got this table up here, so we don't have to rewrite that, but we do need to write the expected count table. And I'll show you how to do that in just a second. Remember that the chi-squared formula is the sum of observed minus expected squared over expected. You do need to put that. All right, so now what I'm going to do is I'm going to show you guys how to write the expected table on your paper. And you have to use your calculator. You have to put these in matrices. All right, so first of all, go to matrix. We have not done that yet this year, so second x to the negative 1 is matrix. You're going to go over to edit. All right. So matrix A. All right, this is a 3 by 2. All right. You do not include the total row or the total column. You only are interested in this part. So that's a 3 by 2. All right, so you type in the numbers there from the observed values: 3, 37, 27, 12, 28. All right, then quit, go to stat, go over to tests, go to chi-squared test, not GOF, not goodness of fit, but chi-squared. And the TI-83 and the 84s should have chi-squared. But remember, I told you guys in the last video that only 84s have the goodness of fit test. So now you'll see it says observed and expected. We only filled out the observed matrix. Matrix A, we filled out with all the data from up here. Expected, this is the nice thing about the 84s, the expected matrix will be matrix B, and it automatically fills it out for you. So you don't have to mathematically figure out the expected counts. The 84 is going to take care of it for you. Hit calculate, and then it solved it for us. Now, we do need to know the expected counts because we just assumed right here that they were all greater than 5. Now we need to double check, and we need to put that table on our paper. So I'm going to go back to matrix, go to B. Notice that it made it a 3 by 2, and we can go over to edit, press enter, and there's the expected counts. Notice that they are all greater than 5. So I'm going to write those down in just a two-way table over here to the side. I'll round to the first decimal place just to save time. All right, so this is the expected counts. And I'm just going to draw an arrow right here, letting them know that these are expected counts. All right. So you always need to put that. You need to put the expected counts because you do have to double check that they're greater than 5. So this is going to kind of act as your data. Now, I don't think that they told us what alpha level to use. So I'll just put right here alpha equals 0.05. Now let's go back to the test. Let's run it again. So the chi-squared value is 4.84. The p-value is 0.0889. All right. Oh, and the degrees of freedom is 2. Now, the degrees of freedom formula is different. You should have read this in the book by now, but it's rows minus 1 times column minus 1. So row minus 1 times column minus 1. There are 3 rows, so subtract 1 from 3, you get 2. There are 2 columns, subtract 1 from that, you get 1. 2 times 1 is 2. So that's why degrees of freedom equals 2. Now, the conclusion. Oh, I left the C out. There we go. Since our p-value is greater than alpha, we fail to reject the null. There's not enough convincing evidence to show a difference in proportions of cardiac events for the 3 treatments. And there you go. So that's the conclusion. That's everything that you need. I did want to state one other thing in this video. I'll do another video for chi-squared test of association / independence, but I just wanted to focus on homogeneity in this one. But one other thing, let's say that there was a part D to this problem that said, what is the expected counts of this cell? Now we know that it is actually 7, and that's just a coincidence. It was 7.000 something or 6.99 something. But if we wanted to do it by hand, they tell you how to find the expected count of a cell value by hand, and it's row total times column total divided by table total. So if you want to know what the expected count is for this cell, you would do 34 times 22, row total times column total, divided by the table total, 107. So apparently 34 times 22 divided by 107 is 7.0. So that's how you do that. So 2 formulas that you need to know for this section is how to find expected counts by hand, row total minus column total. Row total times column total divided by table total. And then the degrees of freedom, that new formula is rows minus 1 times columns minus 1. All right, so hopefully that's covering everything that you need for the homogeneity. And then the next video I make will be for the chi-squared test for association / independence.